Distinguished guests, participants, ladies and gentlemen.
Thank you for returning to your seat and welcome back to the second session of the second day of the 8th SEAMS-UGM International Conference on Mathematics and its Application 2019.
Ladies and gentlemen, proceeding with the second session and without further ado, we would like to invite the moderator of plenary lecture 6, Emmanuel Abio Cabral, PhD from Ateneo de Manila University, to come to the stage. Please welcome.
Yes, we already have.
Good morning. Our next plenary speaker is Professor Dr. Marjono from Brawijaya University. Professor Marjono is currently the director of postgraduate school in Brawijaya University, and he used to be the Dean of the Faculty of Science of the same university, and also the Secretary of International Office of the same university. Professor Marjono was a PhD student at the University of Graz in Austria. His areas of research includes analysis, particularly in the area of harmonic function, modeling on the global warming, Basilevich functions, and univalent functions. Professor Marjono will talk about the coefficients for Basilevich functions, B1 alpha. So without further ado, let us all welcome Professor Marjono.
Thank you very much. Thanks a lot.
You will have time to...
Thank you very much for introducing me. Ladies and gentlemen, Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, good morning. Have a nice time, and already the second day, I think we are still fresh now. And I would like to share about Basilevich functions. I try to find to see Pak Ali Rosian. Is he here? Or maybe Maslina? Yes, thank you. Yes, if I have a hard question, I will need their help. Okay, actually I want to talk about univalent functions, or maybe the similar terms about injective functions. And today, this talk, we work with Janusz Sokol from Polandia, but unfortunately I never met these guys. I only communicate with him by email, internet, something like that until now. And I did with my former supervisor, Professor Derek Thomas from Swansea University, which is now a very big university. Before that, we still in the University College of Swansea, but now become a very big university. Okay, the scope of my talk, actually, we have S here, the subclass of, say, univalent functions, the group of many injective functions, and D here mentioned about the unit days, the days with the radius 1. Then we will make kind of normalizations by take the value of f0 equal to 0 and f prime 0 equal to 1, so that here without a0 and start by z and then continue the series start from 2 until infinity. B1 alpha is a subclass of Basilovich function. Then we only consider about the early coefficient. We know already details studied by Singh from India. Usually he talk about A2, A3, and A4. Then when I went to Graz, it was 1997, I thought, why not I think about A5? Maybe some people doesn't interested that. But why not? Because just for about start, I tried to learn about A5 itself. And then finally, Janos know me, and then he continued with A6, something like that. So the keyword here, univariant functions, which is injective, Basilovich function. So this have special properties, and then in this function, and we only interested in the sum coefficient of them. Okay, we use the domain open connected, and then I mentioned before that the complex value is called univariant if injective. So we only restrict in this talk. We can start with the Riemann mapping theorem, telling us that from the unit disk, which is a subset of the whole complex functions, there is one-to-one maps from this to other unit disks. So what is the advantage if we have this situation? It means we are not necessary to have the whole domain. I mean the domain of the whole complex value, complex number. But enough for me, enough for us to start in the unit disk. The same with this. We can see anything in the screen, not necessary to see others. Also, if you want to see the football competitions, we are focused in the television. We are focused in the screen, not necessary to go somewhere, because that thing, the job of the cameraman, to seek the better views, to seek the better activities. But now we focus here in the screen, we focus in the D. It is unit disk with the radius 1. Of course, with the value like this, f0 equal to 0 and f prime c positive, and we can make it. We can choose that f z equal to 0. Yes, based on that, and then now we try to step forward a little bit to convince again that let S a function of f is analytic and univariant in the unit disk, normalized by this one I told you before, and then by using Taylor series or maybe Maclaurin series, and then this is the very base of the equation, the formulation of the univariant function. Okay. Then the development of univariant theory running quickly when related to the Bieberbach conjecture, I think around 1915 or 1916, something like that. And this inspired by the so-called Kubu function K. K here is the function which is optimum, because if we want to try to find the maximum, and then this guy always come first time. K set equal to z divided by 1 minus c squared. Actually, we can write here like e to the I theta, but we choose the theta equal to pi, 180 degrees, so come like that. And then if we do by expanding the series, we will find that this c plus sigma n c to the n. So the coefficient here exactly n. So this is why I told you this function, Kubu function, have a optimum value. We like it very much. 1916, Bieberbach saw that the modulus of A2 less or equal than 2. And then he conjectured that should be the modulus of an less or equal than n for all n greater or equal than 2, which would be best possible in view of the Kubu function itself. So the idea is this: if we have function and then we can make the expansion of it by writing in a series, but the formulation we already defined, already fixed that. And then actually we want to try to find the growth of its function by knowing about the coefficient itself. Then to know the coefficient, we start from the early coefficient, the beginning coefficient, A2, A3, A4, and then A5, A6. And now we are doing with my student here, Saadatul Fitri, we try to find A7 of this coefficient, and to also to try to develop some other subclass. The conjecture became one of the most celebrated problems of the 20th century. Actually, the first time progress is quite slow. Then 1986, the conjecture had been established only n for 2, 3, 4, 5, and 6. For n greater or equal than 3, the method of proof required the development of non-elementary methods. Others try to find the smallest constant c such that the modulus of an less than cn. And 1976, the best known bound for c was approximately 1.0691, something like that, for that calculation. And then afterward, around maybe almost 20 years, 1984, this is a surprise because the branches found a proof of the Bieberbach conjecture, but his method of proof was far from simple. But it is a good progress. It involves the combined idea from the following areas analysis, which are Hilbert spaces of analytic functions. We know that we start and we work in the injective functions, so we need that space, Hilbert spaces, and try to find the solution. And then also some very clever inequalities about how to turn information about the logarithmic coefficient, logarithmic of fz divided by z, into information about the coefficient of fz itself. Yes, and I think almost similar by using by statisticians, that if we have data and then so big and then we try to find the logarithmic, something like that, and then finally we retransform again or we inverse this function. The use of theory concerning the parametric representation of slit mappings developed by Launer. Why slit? Because this is happen in the whole except some lines, which is usually, it depends on the theta itself from 0 until 2 pi, so that we call as slit mapping. In 1923, proof of the conjecture when n equal to 3, and then the last, an appeal to a result about hypergeometric functions. So these are the things that we need to overcome the problem. And then 1 year later, 1985, Fitzgerald and Pomorenke, which is, he's write a lot about the univalent functions, produced a proof that was independent of functional analysis and published a purely function theoretic version. Yes, this is Pamorinke, and then also Peter Duren, some people who interested in this area. To be honest, that this univalent function usually studied in surround Romania, Polandia, Hungary, in Austria, but here surround Southeast Asia, I think in Malaysia, like Professor Maslina Darus, and then Professor Rosian Ali, and also some friend from Hong Kong. So we are very pleased to try to develop this topic of area. And then I'm very happy that last year I can visit UPM to share about the univalent function itself. And I think we are proud as well that this year in November, 4 until 6, Brawijaya University will have the GFTA conference, Geometric Function Theory 2019, and hopefully it will run very well. Although the Bieberbach conjecture was the central problem, many others were investigated. In particular, assuming that the image domain of FT, where T is unit days, has interesting geometrical shapes, gives rise to subclass of S, which with more tools to deal with leads to a rich source of problems. Yeah, so we try to find what the shape, what the region, what the image of this function. The two most natural geometrical conditions to impose on FT are when F maps T, the unit disk, onto a convex set. Convex set. This is the similar definition with convex. If try to put any 2 points, and then the line which is connected these 2 points are inside the set. The same thing. The idea is that about the convex, and if the FT is convex, so the function we can call it as a convex function. And then, if we try to choose one of two any point, it means we only have the rest, only 1 point free, so we will reach to the star-like function, because one already in the center of the star itself. So we only have another 1 free point, then we have star-like set, so we have star-like functions. So then we denote this class by C for convex function, subclass of convex function, and then ST, or sometimes S with star, is about the star-like function. Okay, then by the normal definition, I mean definition from the properties of this function, and then actually now we have an operational definition. So this is about the star-like function, the real part of set f prime over f greater than 0, and then if we try to again to do about the derivation, then finally we have the convex functions, 1 plus set f double prime over f prime greater than 0. Okay, this is the smallest subclass of univalent function, like convex, star-like, and then we also have the function like close to convex in between convex and star-like. So we have this subclass. But greater than that, we know about the Basilovich function. At the moment, is the biggest subclass of the univalent function. So now we try to find the subclass of this Basilovich. We call it as B1 alpha. B1 alpha. The definition is like that. But if not, I mean Basilovich alpha itself, usually we have something here with to the power of delta minus 1, And then if we take delta equal 1, becomes P1 alpha. So actually Baselevich alpha, we still have some expression here in the square bracket. Okay, this is the idea of how subclass or class of Baselevich function be constructed. So this function satisfies this properties. Real part of f prime z multiplied by fz over z to the alpha minus 1, this is greater than 0. And then I and my student Fitri try to make if alpha equal to minus 1. At the moment we choose alpha positive, but on the other direction, if we try to find alpha minus 1, it means here to the minus 2, so we can like c over fc square, something like that, and we have another subclass. Okay, good. Now, in the plane, we have the value which is in the right hand side of the y ordinate. So we call it as function with positive real part. So function with positive real part of pz greater than 0, we can expand this right as the following. We say Cn is the coefficient of the function with positive real part itself. Because in this domain, this have many properties that we can use to help to support find the solution. So many people have the very good, very deep, very detailed talking about function with positive real part. We shall use the following result. This I think done by Kara Theodori and Toplitz. I can't remember the year. But actually, you see, we only try to find the distance between C2 and C1 square over 2. Actually, we try to eliminate the C2 in the term of C1. And then next, if there are C3, and then we can also have the lemma, which is represent C3 and C2, and then everything in C1. And then if we know that the modulus of C1 less or equal than 2, so become simpler. So this is the idea. The other thing, why here the expression like this? Not C2 minus C1, or not C2 square minus C1 square. Yeah, we only try to work with the simplest one, and then when we try to make some coefficient of them, try to compare the coefficient, and then there is this term. So this is why at the moment we try to find the distance between C2 and C1 square, not the others. This from Kara Theodori, and then also the same idea done by Toplitz. The second lemma we will use there. If P and P, big P here is function with positive real part again. This is Cn, I mean. So sometimes some people try to find the expansion, the series in Pn as well, because function with positive real part. Then here C3 minus 2C1 C2 plus C1 cube less or equal than 2, almost the same, and also C4 something like that. So the idea again, I mentioned that from there finally we will have the expression only in C1 without the greater C. Okay. Also we use if P and P, and then again, sorry, Cn modulus Cn less or equal than 2 for n greater or equal than 1. Now C2 minus mu over 2 C1 square is this, the expression. So you see if mu equal 1 will return back to the first time about character tuplets. And then if we try to mu between 0 and 2 and then elsewhere, we will have this expression of the lemma. These three lemma, that's all. We will use the lemma, and then the theorem we got is this. But actually, this is not so big problem, not so big solution. I mean, not so big topics, because I again only try to increase from A4 to A5. I skip for the A4, which is between alpha 0 and 1 because of the expression of the slide. Sorry about that, because my aim here is to show the A5 here. And you see, there is a model here, A2, 2 over 1 plus alpha, A3, 2 over 2 plus alpha, A4, 2, 3 plus alpha. So A5, I think there will be 2 over 4 plus alpha for the other. I mean for alpha greater than 1. But until now, and also helped by my student, I still can find the exact value until 1. So we only have the alpha 1 here is 0.96942. Calculated by Mathematica software, and I still don't know about the value greater than this alpha 1 until 1, so still open for that. And alpha 1 here is the smallest positive root of this equation, and this all the things here we try to calculate with the software. The important thing now is about this. If we have 3 plus alpha, so okay, thank you. So we cannot directly calculate the interval between 0 and 1. By this, so we should be careful. We should start calculate for the alpha between 0 until 1/3. Until 1/3. And then before that, when I tried the other thing, we sometimes also calculate until a half. So again, first 0 until 1/3, the second one 1/3 until a half, and then the third one a half until 0.9 something. I couldn't do until a half until 1, something like that, because of the properties of the function. Okay, it was about the A5, and then this is about the inverse function. So if we have f, the function from t to ft, which is we say omega, from c to omega, and then we have inverse function from omega to return back to say c. So now we can have another series, like the function will be omega 1 plus a big A something about omega square, etc. So now only try to have another notation from a small a and then to become a big A like that. But the function is an inverse function, and then with the same methods, finally we have the estimation of the coefficient of that. Okay, and then this actually more effort from Janus, not myself. So after I have the A5, the fifth of coefficient, and then Janus from Polandia try to continue that, and we call it as A6. Still the same methods, but only more complicated expression of the function. And then finally have that. So we write an A, B, C, D, E, F, which is this expression. And then next we try to find the optimum of this expression. The third one, moment. That's all. So the point here, I lost something maybe. Here, not, this one, sorry. I forgot to see that. So, to prove the theorem, I mean the three things. One about A5, second about A6, and also about the inverse of A5, pick A5. The standard operation, very elementary operation like this. The first representation in series, like you see, if the function fp1 alpha, it means this is positive. I mean real part of this greater than 0, if positive, so here there are NP set. If there are NP set, and then after this series, and then we try to compare the coefficient. After comparing, we will have some equations, and then finally we try to finish the equations or maximize or minimize the term needed. So that's all, and finally we have the expression, and we know about the growth of the function. I think that's all. Thank you very much.
So, thank you, Professor. Are there any questions to our speaker? We have time for 1 or 2 questions. Oh, yes, sir.
Yes, please, Mas Nanang.
Thank you very much for the time. I am curious about the bond that you said that the bonds are sharp, right? So does it means that the bonds is the smallest upper bound? If so, then is there an explicit nice function that attain that bond? Thank you.
Thank you. Very good questions. Yes. So yeah, the idea implies the least upper bound, and subs, I mean about the maximum one, and then if not, so not upper bound anymore. And the function itself, yeah, both Kubu function I mentioned, c divided by 1 minus c square. This is exactly the function which is satisfy the properties and really equal, not least, but really equal that things. Yeah. Okay. Yeah, at the moment for this, we try to the alpha positive alpha. But the other thing about the alpha minus 1 I mentioned, but not here, we try to still work with my students now, but we have not checked yet. Yeah.
Thank you, sir, for your question. Any more question?
And while waiting for the question, I mean, we try to extend from A5, A6, now A7, but also we try to expand the subclass. For example, we try to have maybe P1 alpha lambda, because actually P1 alpha is P1 alpha lambda whenever lambda equal to, I can't remember, 0 or 1, yeah, and then like that. So, okay. Yes, please.
Okay, thank you, Professor, for that answer. So, if there are no more questions, let us again thank Professor Marjono for giving him another round of applause. Thank you, Professor.
Thank you.